Okay, so lecture 2. So this is where we move into a bit of the mathematics of the subject. It's not scary mathematics, okay? It's stuff that you should be very familiar with, simple trigonometry, basic matrix algebra, as I explained last week. This is not a mathematics class, so I'm not going to cover any of the mathematics I present. I'll present it as a tool to be used. I'm not going to start explaining how all the rules of matrix algebra, some of the trig that I will use, such as cosine formula, etc. I'm going to expect you to know these. Okay? Why are we interested in coordinate transformations anyway? For all our robot systems, hope you can all see this, they're going to be fixed in space. Okay? And the position they're fixed to in space will be assigned a set of coordinates. Okay? Now I should have kept hold of my robot. And our robot will be fixed to the home of that set of axes. Okay? And what we're looking to do, so imagine the red tape on the end of here is the end of the robot where we attach our tool. What we're looking to be able to do is configure our robot within its work envelope that will position the end of the robot, so the wrist of the robot that holds the tool, anywhere in space. Okay? What we'll ultimately end up doing is assigning a set of coordinates to that end of the robot. So the robot model going around, imagine this is stuck to the end, and this will move through space with the robot. As we reconfigure or pose the robot, it'll move through space, attached to the end of the robot arm, using the major axes. So if you just can move this with the major axes, this stays aligned with the home coordinate system. Okay? So the three major axes allow the translation along the three orthogonal axes. Okay? So that will move around. This is the end of our robot arm, where the end effector is attached. The 6 minor axes will then rotate and orientate the tool that's fixed within this frame somewhere within, or orientate it to the work envelope. So the 3 major axes move, this is not going to work very well on the recording obviously, will move around in 3D space and remain aligned with our fixed coordinate system, fixed at the base of the robot. The 3 minor axes will rotate with the robot joints to allow us to align whatever's attached here with our workspace or within our envelope. Okay? Does that make sense? Yeah? So for the most part of this module, the bit I'm doing, we're only really going to be looking at the 3 major axes that allow the robot arm to position the end effector somewhere in space. So we'll be looking at where this end effector coordinate system moved to as we configure the robot. So as you get hold of the model, there are 3 major joints. As you move them, this will move in space, but it will remain aligned with our coordinate system. Okay? So why do we need to work out coordinate transformations? And again, all this will become clear. But what we need to do is, when we're looking to tell our robot to move to a point in space, it's always with reference to our fixed coordinate system. Okay, we need a fixed reference, so we'll always say move to a point x, y, z that's relative to this coordinate system. As you'll come to know, as we look at our robot, we're going to assign a set of axes at every joint that are aligned with the joint, and we will start at the one on the end, and we will know within this coordinate frame at the end the position of any point within it relative to here. Okay? So relative to this coordinate system, we can position a point in it. So think of this as A, B, C. This is X, Y, Z. A point within this one could be described by A, B, C. But then if we want to take that point in A, B, C and describe it with this point, within this coordinate frame, X, Y, Z, we need to know what the transformation from this frame to this frame is. And that's a simple matrix. And we can use that matrix to position the point in here with respect of our fixed base coordinate system. It'll all become hopefully clear as I go through this. Okay? Ooh. So first two we've done now. So we're now into the knowledge and fundamental concepts in robot kinematics and control. So robot kinematics is really the study of movement, how the mechanical structure moves depending on how it's configured with its joints and links. So this is the model I'm moving around. Sorry for the poor photographs, it was still from a video. We have the base of the robot. This would be fixed in space within an industrial setting. That does not move. It's bolted to the floor. There is then a revolute joint here, whose axis of revolution is vertical. So that allows the robot arm to move around that axis. And so this bit would move into and out of the page. So it's vertical. Axis of revolution is the first joint on the base. And then the next one up, there's a bit of a link here, and the next one up then is another revolute joint, but the axis of revolution is out of the board towards you, for example, which allows that arm to move, rotate around the horizontal axis, will move up and down, okay? And then we move to another revolute joint here, whose axis of revolution is again out of the board, and that again allows that link here to rotate in the plane of the board about the axis if it was out of the board. Okay? So the base one allows kind of the movement this way. Then you have one on what we would call the shoulder here that allows this link to move up and down around an axis of revolution coming out towards you. And then we have another joint, which we can consider the elbow here, that allows that final link to move up and down. So that combination of the vertical rotation and the two horizontal ones allows that robot arm that's moving around the room to position its end effector anywhere within its reach of the robot. Okay? All makes sense so far? Yeah? So why are we doing this? So that's just a bit of background to get you thinking about how this looks in terms of 3D space and getting things moving. So the motivation for this is we can only describe the position of an object, right? So we can describe the position of an object by giving it a set of coordinates. If you think back to what I covered last week when we were talking about how many degrees of freedom a rigid body has in 3D space, for example, 6 degrees of freedom, but we can describe its position in space via set coordinates x, y, z. So we can only describe the position of an object. For this module, the object is the tool or end effector or the wrist of the robot, where we mount our tool or end effector at the end of the robot arm, with respect to some agreed reference coordinate frame at its base, which would be this fixed coordinate frame. So our end effector, to position that anywhere in space, it's always with reference to here. So we would say go to x, y, z, and that's where the robot would go to, would configure itself, configure its joints to reach that point in space. We need to be able to direct the tool to point in space and have the tool interact with another object. So anything the robot interacts with, anything you want the robot to pick up, for example, also has to exist within or be described with reference to this fixed base coordinate frame. Okay, so I'll refer to this as the fixed base coordinate frame for our robot from here on in. And the frame of reference for us will be the one whose origin is at the fixed immobile base of the robot. Okay, so it's the base frame or world frame. Okay, for us the base frame and the world frame will coincide. Okay, but the important thing for this analysis is this fixed base frame where the robot is fixed to never moves. So we need to come up with an approach to controlling a robot. So we need to create a kind of algorithm based on a computer model of a robot. And so for our purposes, as I described last week, a robot is a chain of links and joints. Okay? So the links are the solid, rigid, they don't deform, they don't bend elements between joints. So a joint at the base, joint at the shoulder, joint at the elbow, joint at the wrist, and then through the tool. Okay? Key for this, links are rigid and inflexible. If they did flex, that's going to give us an enormous amount of problems. Joints for us in this module will constrain movements to 1 degree of freedom. Okay? So a revolute joint whose axis of revolution is out towards you will only allow movement in the plane of the board, for example. It can't go in and out of the board, it can only move in one direction, okay, in the plane of the board. So we've constrained the movement of whatever's attached to that revolute joint to only be able to rotate. Can't move up or down, can't move in and out, it will only rotate in one dimension. There. And then we have one end of the robot is the base, and that's fixed, as we've said, and the other end is where we mount the tool or end effector. It really determines what the robot is capable of doing. So this is just a line drawing of a robotic system. And this is a small desktop robot called a Dobot, which you'll come across in the coursework. Yeah.
Would you say there's a joint in the tool, or would you not count the thing that's making the hand move?
No. So you could have a servo or something that opens and closes the joint, the gripper, but it doesn't add a degree of freedom to the robot. It will only open and close the gripper. So when you come to do the coursework, you might have to tell me how many degrees of freedom this has. The actuator for the arm, for the claw, will allow it to open and close, but it doesn't add a degree of freedom. Okay? So this is a real robot, so it's the same configuration as this. So joint in the base, shoulder, elbow, and then there's one at the end. The configuration of this robot's a bit odd, as in this end piece here will always remain parallel to the ground as the three major joints move around. It's kind of like a pallet, it's called a palletizer type robot, and it's really for moving wooden pallets around and stacking them. So what you don't want is to move a pallet and then be off at an angle. So the mechanism within this always means that this part always remains parallel to the ground. Okay? So you never have to adjust the orientation of the end effector with this robot. Everything is always parallel to the ground. And this is the robot you'll use for the coursework. So you'll be given a couple of tasks to do, a bit of analysis, and then you'll program it to complete a task. Okay? So the objective for us is each of these joints have 1 degree of freedom. So each of these joints have one parameter we can change. So for a revolute joint, that's the amount of rotation. For a prismatic joint, which is the other joint we're going to consider, it's the amount of extension or retraction along a linear axis. Okay, so again, 1 degree of freedom, it's either towards you or away from you, never up and down, unless it was vertical, then it would be up and down, but never then towards or away from you. So revolute joints, prismatic joints, one has an angle of revolution as the variable, the other has an extension or retraction whose variable we label D. So the object of our mathematical approach is to analyze the robot and come up and form a relationship between these joint variables, so theta, which is the angle of rotation, D, which is the amount of retraction extension, formulate a relationship between the joint variables and the orientation of the tool, so the position of the tool in space and its orientation of the tool. But as I've said, what we're really focusing on in this is positioning of the tool tip in space, not the orientation. Okay? Analysis is exactly the same, it's just more involved. Okay? So you're not missing out anything there. If you want to go to the effort of doing a full robot major minor joints, you can, using exactly the same approach is that I will describe in this module. So given theta, given D, where theta is the revolute joint variable, D is the prismatic joint variable, we want to find a formula that relates the tool coordinates. So that's the coordinates of the tool that we want to position, or we position in space, with the base or world coordinate system. So we configure our robot, we set all the joint angles, where is the end of our robot located in space, and how is that position related to its fixed base coordinate system. If you finish with the robot, can you pass it through to the next section, please? So throughout this, we're going to use concepts or principles of Euclidean geometry. So everything's based on 2D geometry, so stuff you would have done in high school and first year of maths here probably. And for our purposes, in 2D, a point in space can be expressed using two coordinates. But in general, a point is located in n-dimensional space, so we need n dimensions to describe our point in space. For us, we'll be in 2D, so we need two variables to describe the position of that point in space. When we move to 3D, we obviously need three variables. So this should not be new to you. So 2D geometry, we have a point P, and it's described by a vector AB, and it describes its location along the x and the y axes. Okay, very simple. So we can describe point P as a vector. For this module, all vectors will be bound to a fixed coordinate frame, which just means this is always fixed. This never moves. Okay, so if we describe a point P using a vector, AB, it's always fixed to that home position on our fixed coordinate frame. Okay, we don't have things moving around. So 2D geometry, points define a location. You can't sum or multiply points. So again, this is all just a recap on stuff you should already know. Vectors do not define a location, but you can add, subtract vectors, multiply by a scalar. Difference between 2 points is a vector. A point's location is defined by a vector displacement from another point. So these are things that you should know. You just need to have in the back of your mind for this module. Whoops. So now on to kind of the important stuff. Throughout your course, you may have come across coordinate axes, right-hand rule, left-hand rule, defined positive directions of rotation. We have 2 rules within this robot, and 2 conventions that must be followed, otherwise you get the wrong answers. Okay? In the real world, as long as you follow a fixed set of rules, you'll get an answer that will work. But if you're working in an engineering practice where one of you is using a left-hand coordinate system, the other's using a right-hand coordinate system, everything's going to go a bit wrong. Okay? So throughout this module, we're going to use a right-hand coordinate frame, and I will pass out these later. These are like an aide-memoire, something you can look at if you get confused what a right-hand set looks like, where x is, where y is, where z is, for example. And these you can take into the exam as well, which saves you doing all manner of contortionary things in an exam to try and work out the answer to one of the questions. Okay, so we're going to use a right-hand coordinate frame. So for rotation, the right-hand rule is right hand, place your thumb upwards, and you curl your fingers around your thumb, and as the motion of curling your fingers defines the positive direction of rotation. Okay? So, axis of rotation, right hand, thumb along the axis of rotation, curl your fingers, that is the positive direction of rotation. Okay? So, if we have that here, so that's our XY coordinate system. The axis of rotation is coming out towards you at the origin. Thumb along the axis, curl your fingers round, and the positive direction of rotation is such that it will rotate x up to y. Okay? So that's very important. Don't get that mixed up and do left. Left-hand rule, always right-hand rule, and the direction you curl your fingers in is always the direction of positive rotation. Okay, that becomes quite important later on. And you must be consistent in the application of coordinate frames and always use the right-hand set in this module. I have come across other modules even that talk about robotics as an example, and they use left-hand rule. Right-hand rule is where we're going with this one. Okay. So that's the right-hand rule for rotation. We have another rule where we will use throughout this module right-hand coordinate frame. So again, that's really, you can do this by positioning your fingers, thumb up, forefinger out, and then middle finger orthogonal to both of those, and that will define your x, y, and z axes. And then what we find in an exam, everybody is doing this and whatever, and getting it a bit wrong. which is why I produce these, so you don't have to do that. Okay? So I'll hand them out later on. So, this is kind of touching on what I've already covered. So we have a robot. It's at the base of our coordinate system, fixed there. It doesn't move from there, but we compose the robot to allow it to interact with whatever's in the environment. Okay? So we want that robot to reach that point, or be configured to reach that point in space. Okay? And that point in space may be assigned. Okay, what have I done here? Right. So that point in space will have its own coordinate system assigned to it. This will become clear in a minute what I've done. And there will be a point in that space that will have another coordinate system assigned with it, and there will be a point in that space that will have another coordinate system assigned to it. Okay? And what we want to be able to do is come up with a relationship between the position of this, which we know within its own frame, but we want to be able to relate it to a position within our fixed base coordinate system. So at the moment, this frame, with its point here, can move anywhere here in its own free will. That will move this frame with it, and then this point can move within its own frame. So the thing's all kind of fluid and moving around, and it's going to be very difficult for us to position this point P with respect to this fixed base coordinate system. So what we're going to do now is, so there are no constraints within this because these points can move anywhere of their own free will, etc. Now if we apply some constraints where we fix this point here, it can only move relative to this joint and this fixed link. And then we have, at the end of there, we have another frame with this point in. So as we move this link that we've constrained to only rotate around here, this frame will also be constrained in its movement. And the movement of this point within its frame is also now constrained because we've added another link here. So whereas before this point could move anywhere within its frame, and this point can move anywhere within this frame, we've now constrained it by adding a link to a joint at the home of each of those coordinate systems. And then we extend that again to our final link, where again we have a point moving, but we've constrained its movement, how it's allowed to move within that coordinate frame by adding it a link and a joint. Okay, so that is probably, you're thinking, all a bit confusing. So what I'm going to do now is I'm going to develop this theory through initially simple trig. Then I'm going to extend that to a matrix formulation that will allow you to work out, given the position of our end effector within its own frame, how we go from its frame to the frame before, and finally come up with a set of coordinates relative to our fixed base coordinate system. Okay? Right. All will make sense. Somebody want to open that back door for me? Because it's getting a bit warm. Need a bigger lectern. I'm just checking and projecting what I need to project. Okay, so some of what I say is going to be a bit of a recap on what we've already looked at. But again, bear with me. So again, if you've any comment on my approach from now on in, if you don't get it, please let me know. Okay? And that's with the way I'm presenting. So, is that big enough for everybody to read? Yeah. When I start to get to the bottom of the page, if I'm happily writing away and talking to myself and I've gone off the page, please shout and tell me to scroll. Okay? So, okay, so I've already mentioned that. So kinematics is a study of movement, and for our purposes with the robotic system, we're interested in how the robot moves and configures itself and adopts a pose based on the information that we give it to determine what that pose is, so either the point in space that we want it to reach or how it should adjust the angles of its joints. So the two approaches we're going to consider are forward kinematics and inverse kinematics. Okay? I'll go on to describe what these are in writing, but forward kinematics is that we look at our robot, we tell the robot what the variables are, so how much revolution we apply to each joint, how much displacement we apply to a prismatic joint. The robot will configure itself to those commands, and that will position somewhere in space the end effector. Okay? You may argue that's not very useful because you always want to know where to position your robot in space, but it's useful for part of the control system that I'll mention somewhere down the line and further analysis. But forward kinematics is we say, set your shoulder to a certain degree of revolution, say 45 degrees, yeah, and set your elbow to a certain revolution, say 45 degrees again, and then I can calculate where my hand is in space relative to whatever my fixed coordinate system is. So forward kinematics is, whoops, yeah, that'll do.
Basically, controls.
It's used for that, yeah. What's it doing? Right, yes. So it'll come in for David's thing in the last 3 lectures, so, and I will discuss that. So, right, forward, given. So joint variables for us are theta and d, so we won't change those joint variables. If there's ever a theta, you know it's an angle of rotation. If it's a d, it's an amount of displacement. So given the joint variables, calculate the end effector mount point. Okay? So I'll just pick up on that point about the control side of things. The other approach is inverse kinematics, where we pick a point and calculate how the robot should configure itself. What we can do is, once we've positioned the robot where we want it, we can then kind of backtrack, we can do the forward kinematics and make sure all the angles are set to where they should be, because you'll have feedback, you'll have sensors within the joints that tell you where they're positioned as they should be. And it may be that you, based on the errors inherent within your robot structure, you can make very small adjustments as well, using both, okay? And again, I'll pick that up again. So what we're going to do, we're going to consider a very simple robotic system first. There's a planar robot, so it exists in 2D. Planar robot, so all the movement is in one plane, and that's going to be the plane of the board. Okay, so that's just basically writing out what I've just said. So what I'm going to do now, I'm going to do a sketch of the robot. I'll do the robot at rest. And when I sketch a robot that's at rest, it means I haven't applied any amount of revolution to my joints. So for all intents and purposes, if the robot was to interrogate itself, all its joints are set to 0 degrees. Okay, so that's our fixed base, fixed frame coordinate axes, so labelled there y0, x0, that's our origin set of axes. Okay, and there are two links. We call them link 1 and link 2. We have a revolute joint base, revolute joint at the base, and a revolute joint at the middle of those two links. Okay, so that joint holds those two links together and stops the end link from just wandering around all over the place. Okay, so revolute joint here that allows this joint to move, rotate around it. As it rotates around it, it will carry this link at the end, but this link can also rotate through this joint around the end of this link. What's the positive direction of rotation for link 1? We have one for counterclockwise. Any difference of opinion? Yeah, we'll go with that then. Excellent. Really? So. Okay, so that is our theta 1, that's our joint variable, and likewise for the second joint, theta 2, and that's our second joint variable. Okay, and what we're going to do is the point at the end that we're interested in locating, the position where our tool will be or end effector, we're just going to label point P. Okay, and for our purposes, L1 equals L2 equals 1 unit. And P equals the coordinates of the end effector. Okay, so the end effector here, that we don't have anything, where we just have a place where we can position something to do something. So it could be a gripper, for example, it could be a pen, but that's whatever we fixed to the end effector, that will be described, its position would be described by P. Okay, so all joints are revolute for our purposes, and at rest, okay, so that's the situation. That's our status at rest. Both joints are set at 0 degrees. Not always the case with a robotic system. You might have a robot whose joint has to be offset for some reason or another, so you may have to take into account that the joint, even before you start moving it, has to have adopted an angle of say 90 degrees or something, and you need to factor that out. That'll come into play a bit later on. Okay, so that's our situation at rest. What we want to do now is we want to position our point P somewhere in space. So we want to pose our robot to allow it to have the position of the end effector somewhere in space. Okay, so we've positioned our robot such that we've instructed it to, whoops, go on. Our first joint to set an angle of positive theta 1, and then the second joint to be at an angle of theta 2. Okay, now at rest, this joint was in line with this dotted line here, so it was in line with the first link. Okay, so if you look back to that figure, they're both aligned. Okay, so an amount of rotation would be relative to that start position. So kind of and think of an axis extended from this link going outwards. That would be the rest position. We apply an angle theta, and then the robot adopts that configuration. Okay. So for this analysis, that has to hold, so we're not moving the origin of our coordinate frame. Okay, and P is the position of our end effector mount point, which is the end of that link, with respect to our fixed base coordinate frame, x0, y0. So once we pose the robot, remember this is forward kinematics, we set the jump variables and we want to know where the end of our robot arm sits. So we need to calculate the position of P with respect to our fixed base coordinate frame. So that's the process I'm going to go through. Okay, so that's just really restating what I've already said. Forward kinematics approach, we need to calculate the position of point P with respect to the fixed base coordinate frame, which is x0, y0, and that's a position of the end effector, knowing the joint variables. So for us, it's θ1 and θ2. Okay, so I'll pause there for a bit, and we shall come back in 10 minutes, okay? So just before we hit the hour, 4 o'clock, if you could be back in, if you need to stretch your legs or anything. Okay. Can we start again then, please? So, where have we got to? So we've created this simple robot, two-link planar arm. So it's just two links joined together, or joined or fixed to the origin by a revolute joint, which allows it to operate in the plane of the board. And then there's a link that's fixed to a further link, and at the joint between those links we have another revolute joint, allowing that link at the end to revolve in the plane of the board whilst attached to the end of the first link, okay? What we now need to do is come up with a way of calculating the position of our end effector mount points, our point P, if we know θ1 and θ2, okay? So the first thing I'm going to go through is a very simple trigonometric approach. So this, again, this is really high school stuff, first year algebra at worst, trigonometry at worst, okay? To allow us to calculate the position of point P, knowing our joint variables. So that's our configuration, okay? So what I'm going to do now, I'm just going to start labelling that up, and it'll allow us to work out the position of our end effector given our joint variables θ1 and θ2. So we know the length of the link here is L1 and L2. So if we just draw some lines on, if we know L1, we know θ1, I hope you'll agree, we can calculate the position of that point of that revolute joint in the X0, Y0 frame, okay? So nothing difficult about that, hopefully. So, someone want to tell me what the horizontal question mark is? What this one is? Sorry? Oh, right, I thought someone said sign. Right. Okay. Okay, so hopefully everybody will agree with that. I've drawn this badly. So that angle I've just pointed to there is... That is going so well. Okay. So from that we can work out now the coordinates of point P with respect to our fixed base coordinate system. Nope. Not what I just said, sorry. Okay. So we can now work out two other dimensions based on, so again, simple trig from what we know, that total angle that I've just drawn in is θ2 and θ1. So, don't want that one. Okay, that's that bit there, and the file is... Okay, so now we have enough information to calculate the position of our point P with respect to our fixed base coordinate system. Okay. So that's with respect to Okay? So given everything we know about our robot, we've set the joint variables to theta 1, theta 2. That allows us now, from those two expressions, to calculate the position of point P with respect to our fixed base coordinate system. Okay? So that's relatively easy, well, very easy for a simple 2D case. But as we extend the problem, it's not very convenient. So if you think about what I've done there, and if you add more links to our robot arm, you take it to 3 to 4, things are going to get quite messy trying to work out kind of the position of our point P given all those joint variables. Okay? Okay, so if we move to more complex situations, it becomes a lot more difficult to do. And then if you start thinking about what's going to happen in 3 dimensions, when that 2-link robot arm acquires another dimension and is able to move in and out of the board as well as in that vertical plane as well. So the whole vertical plane rotates at the same time. So it becomes very difficult. Okay, so we need a more convenient approach, we need a more general approach that we can apply, and it just so happens that this more convenient approach is based on matrix algebra. So what I'm going to do now, I'm going to take what I've just done and I'm going to adjust what I've done and take it towards a kind of a matrix-based approach. And matrix-based algorithms are quite nice to, or very well adaptable to programming into software on computing systems. Okay, so I still got that there. Cool. Just adjusting this to make it a bit more friendly to draw. So that's our robot arm, okay? Position point P. And we have the robot arm sits within its own frame. So the first joint here sits at the origin of the frame, and the whole robot moves within that frame. What we're going to do now, and what we'll do continuing and forwards, is we'll assign a frame to every joint within our robot system, okay? For the 2D situation, quite easy. As you'll come to learn as we move forward and get into 3D and we do some other approaches, then a number of rules will come into play to decide how we're going to place our frame. But we already have a frame for this joint, we're going to place a frame for this joint, and the rule for this in a 2D system is quite simple. What colour? is the x-axis for that frame will follow the direction of the link, okay? So it'll be collinear with the link before it, okay? And we'll give that x1, so that's frame 1, so frame 0 to frame 1. X axis is collinear with the link before it. So as this link moves, as this joint rotates, X will also move. It's fixed to the end of the link, okay? So it will move with the link, so that x-axis will always be collinear with that link. And that means our y-axis is, anybody want to give a guess? Whoops, we'll take that one. Okay, so that's our y-axis. Call that y1. So that coordinate system moves with the link it's attached to, and then link 2 moves within that coordinate system. Okay, so link 2, revolute joint here, moves within that coordinate system, and that coordinate system moves as L1 rotates, okay? What we can say is we can describe point P within that coordinate frame, x1, y1, if we know theta 2 and L2. Okay, so what I've annotated there is the position. We can denote point P within that frame x1, y1 as the point py1, px1, py1. Okay. Okay, and then I've just drawn on some dotted lines to represent the point P with respect to x0, y0, and we've also got the point P with respect, within its frame, respect to px1, py1. What is missing from the last one? And that was, and we know, as we discussed before, that is theta 1 as well there. So that's the situation. So what I've done there is assign the frame to the end of link 1. Link 2 moves within that frame. We can calculate the position of the end of link 2 using simple trig within its frame if we so wish. Okay. Okay. So the aim of our approach is the same now. We want to find the coordinates of our point P with respect to our fixed base coordinate system, so that's the x0, y0. Okay, and that's always going to be the aim for our analyses, really for forward kinematics, is given the joint variables, we're always going to want to find the position of our end effector within our fixed base coordinate system. Okay. Lost my diagram. So, just going to skip back. I'm just going to number a few things. So, call that 1 and that 2. So from equation 1 that we developed through the simple trig, okay, so what we're looking to do is kind of simplify things, manipulate things using the rules of trigonometry. So we have okay, so that's a cosine A plus B, cosine addition of two angles, sum of two angles. Therefore, okay, when you get to the exam, it's not going to be a memory test. I'm not going to expect you to, if I expect you to kind of derive something like this or demonstrate something like this, prove something like this, I'm not going to expect you to know all your trig identities and everything and remember those. You'll get those on a formula sheet. Okay? So just bear that in mind. This is not a memory test. It's really about how you use the tools you already have to do some engineering, cool engineering things. Okay? Okay? So where those come from is because L2 rotates within its own coordinate frame x1, y1, we can calculate the position of point P, so Px1, y1, within its frame using the simple trigonometric approach that we've already used previously. Okay? Okay, so if we use that fact we wrote above, that px1 is L2 cos theta 2 and py1 is L2 sin theta 2, and we look back at equation 3, we can see that that kind of simplifies, or we can be rewritten as px1 cos theta 1, so just simple substitution into that. And I am going somewhere with all this, I assure you. Five. And then we go through the same process again to come up with an expression for py 0. So I'm going to go quickly through that. So similarly, okay, almost there. Pen's falling apart. Okay, so we have two expressions, and you may ask at the moment where this is going. Two expressions for px0, py0. We've obtained them through more or less the same process. Okay, so what we can do now is take 5 and 6, and we can look at those and we can re-express them, rewrite them in kind of matrix format. Okay, so we place them in a different format, and then we can create our solution from that. So we take 5 and 6 and we rewrite. Okay, so we've got two expressions, and we can re-express that, rewrite that in form of matrices. So, okay, so that's expressed the problem in the form of matrices. I've reorganized some of it just to make things a little easier to explain on what that matrix representation actually means. So if you look at that problem, as we change theta 1 and theta 2, this frame moves, and as it moves, it rotates, okay? So it's rotated with an amount relative to the fixed base coordinate frame, so we need to understand how much rotation that's gone through. And also, the origin of this frame is translated with respect to the origin of our fixed frame as well, okay? So we've translated and we've rotated. So we need to accommodate or be able to describe both of those actions or those operations. And if we know how much it's rotated and translated with respect to our fixed base coordinate frame, we can apply that to this point P within its own frame and yield its position within our fixed base coordinate frame. Okay? So what we need to do is come up with something that describes that to us. So we know the position of point P within its frame, but the origin of its frame has been translated in X and Y and rotated within X and Y as well. So we need something to describe both of those actions. So we have a number of things contained within this formulation. So the first is a 2 by 2 matrix that describes the rotation of frame X1, Y1 within X0, Y0. Vector then, so the 2-element column, is the translation, or describes the translation of origin of X1, Y1 in X0, Y0. And the final vector there is the position of P in X1, Y1, okay? And if you look back, we have expressions for PX1 and PY1 that's a function of the length of the link and the angle of theta 2, okay? So given the lengths of the links, given the angles, we have enough information to work out the position of our point P within our fixed base coordinate system by solving this matrix problem. What is the problem? Okay, put your hand up if you think you know what there's a problem. Okay, a few of you. Okay. Anybody want to say what the problem is? Anyone shout out?
You can't multiply those two matrices?
Yes. So the problem is it's not a valid matrix operation at this point. Okay, so that's not valid because we have more columns than we have rows, so that multiplication does not work. Okay, so we've gone through all that effort and we've come up with something we can solve. Okay, so what do? Let's play some tricks. So, So what we're going to do, we're going to look at that matrix formulation. We're going to add another row that, whilst changing its appearance, will not change our intended result. Okay? So we've come up with a matrix formulation for the problem we're trying to solve, given our joint variables, and we know the physical parameters of our links, which are simply the lengths in this situation. We can plug all those values in and calculate our px0, py0. Okay? And that matrix approach contains both the rotation and translation between two frames in our problem. So I've used the terms between two frames there because as we move past our two-link planar arm and we add more links, we add more frames. And we could have a situation when we have several frames, we start the one with the end effector, and then we work backwards through our robotic system, calculating the transformation between the end frame into the frame before it, into the frame before it, into the frame before it. And all those transformations are included within a matrix that describes the translation, rotation, or transformation between frames. And again, we're going to apply this to a few examples anyway, just to make it more clear. But the matrix that we come up with Okay, so we've come up with a transformation that's taken place between our frame x1, y1 and x0, y0 that we were looking at earlier. So homogeneous, because it's a combination of both rotation and translation. And for all our robotic systems, we're going to come up with a homogeneous transformation matrix that allows us to transform between frames assigned to our robotic system. Okay? So I'm just looking, I've got several examples to go through. I'll do the first one, then we'll call it a day. It shouldn't take too long because it's simple 2D planar arm, but we're going to apply this approach to that. For a 2D planar, so for a robotic system, when you move in between frames, you come up with a homogeneous transformation matrix for every set of frame transformations. So in a 3D system, those matrices could be different. Okay, so you have a whole series of them. For a 2D planar arm, they're always the same because you're always rotating within the plane of the board. Okay, and for a rotation in the plane of the board, a rotation of a point in x, y, that is the rotation matrix. That's something you should have come across before in the mathematics modules anyway. So, I'll do a quick example, or at least part of anyway. So it's the same configuration that we've already looked at. And this will pick up something else that's, and again, I'll always talk about how this relates to the exam and kind of the level that the exam will be pitched at and things you need to be aware of. So I'll never pick on awkward numbers, okay? So for this problem, L1 equals L2 equals 1 unit length, okay? And the angle of rotation is going to be pi by 4. So they're kind of typical of what I'd put in an exam. I'm not going to ask for any crazy angles or put in any really obscure lengths of the robot, make things difficult for you. So do look out for that when you're in an exam type situation. Yeah?
You mentioned pi by 4 is the angle. I'm assuming that's in radians, right?
Yes. Yeah.
In radians,
Yeah.
right.
And again, sometimes I'll switch to degrees to just be consistent. Yeah, okay. So the problem is, as we already know, need to find So we developed the HTM. As I said, the HTM may be different from different robotic systems, different combinations of joints and links, etc. but we've already developed the HTM for this robotic structure, okay? And as I said, that HTM actually applies to any two-dimensional planar link arm, no matter how many links it may have. Okay, that's just a general statement is what we're trying to do. We're trying to place PX or the point P within our fixed base coordinate system by looking at how frame X1, Y1 is transformed into frame X0, Y0. So we take that generalized expression and we write that in the homogeneous form. I'll always spell that wrong. So remember L1, L2 is 1, so I've dropped those out, I haven't included those. Okay, so don't do that. Okay, so that's just a note of where that vector on the end has come from. Okay, so we do have a position within that frame of point P or relative to that frame. So if we rattle through the matrix multiplication, so in an exam you will be expected to do simple matrix multiplication. So this is 3 by 3 matrix. You will go up to 4 by 4, but no more than that in the final exam. Okay. but again, the numbers will be kept relatively easy, so. Stop it. So when we get to that point, so we've worked out px0, py0, 1, so we have a vector equals another set of values. We simply ignore that bottom row that we added previously to make the mathematics doable, to comply with the laws of matrix algebra. And the final result is okay. And if you want to convince yourself that that is correct, yep.
Where'd you get 1.707 from?
Have I done it wrong?
Sorry, scroll up. It might just be a sign mistake or something. Because I thought 0.5 plus minus 0.5.
The minus 0.5 is 0, and that should be a positive 0.
That should be
Which one? Second one.
Yeah.
All right, I'll give you that. Keep an eye on me. If you want to convince yourself, because I knew the answer was right, that's what the pose of that robot should have looked like. So you can look at, so that's 1 pi by 4, which means that's 0.707. And then that is 1.0707. Okay? That touches on a final point. When you're, and again, keep speaking about the exam type situation, and you need to check something, you always you create your analysis, and then you pose your robot in a simple configuration to allow you to check it, so you can quickly throw in simple numbers and check it is where it's supposed to be, which could be put it at rest, set all the angles to 90 degrees or something. So you put it in a pose that you can quickly use to check your results. And again, I'll talk more about that as we go on anyway. So I've got a couple more examples to go through to kind of reinforce what I've done here, to show how you can extend the approach to multiple links, and then we're going to move into 3 dimensions. Okay, thank you.